So what we've done here is that I've said if I made this one's sticking out and that one's sticking out, forget your models now, and we said this one's R and this one's R. Agreed? Okay, I'm going to call that number 1. I have no idea which stereoisomer it is. Now, if I were to draw something that's different, supposing if I were to put this back, knowing that it's R when bromine is sticking out, what would this one be? S, okay. And let's stick this one out. What would this one be? R, okay. So this one is 2R, 3R. Somebody keep an eye on me. 2S, 3R, is that right? Okay. And number 3 now. How about if I do it this way? This time, this one still goes back. And let's push this one back. No, let's do that one. What would that one be? R and S. Now, for those of you, hopefully this is a light bulb moment. You know, I don't need to go back and assign everything again, do I? Because all we've done was switch the wedge and the dash. So you can quickly, yeah, and this is as important as the definitions. Once you've got a diagram down, you can quickly infer the opposite stereochemistry. Are we okay? So what did I say this one is? 2R, 3S. Okay? And then number 4. Okay, which one am I missing? Down, yeah? I can tell who's written the notes ahead of time. Yeah, good job. This one would be S, yeah? 2S, 3S. Okay. So in a nutshell, that's all it is, isn't it? A couple of things. Okay. How many chiral centers do we have here? We have 2 chiral centers. Okay, and we have, how many stereoisomers do we have? 4 stereoisomers. And now let's look at their relationships. You know, when you have 4 of them, they can't all be mirror images of each other, can they? No, it's not possible. Mirror images only generate one opposite. Okay, so when you look at this one, okay, with your 2R and 3R, okay, if I were to say to you, I know some of you can see it, these two, oops, let's change color, yeah, these two, what's their relationship? Are they mirror images? Okay, who cannot see that? Look at it like this. So what I've done is, and we'll see it in the book in a minute. Now I don't know whether this one is, you know, number 1 or 2. It doesn't matter. And hopefully you can see the colors from where we are. You see now, are they looking at a mirror? Okay. Holding it up, they're looking at a mirror. Yes, they are. The mirror is right down here. All right. Or I could turn them and face this way. You got me? Okay. Can you see that the green, there you go. Green and the red, yeah, they're out of alignment, aren't they? Okay. But, so therefore, they cannot be enantiomers. But they clearly are stereoisomers. Why are they stereoisomers? Try again. That will give you half the point. Yeah? Why? Why are these stereoisomers? She's got half the point. She said because there's 3-dimensional difference.
They are on the same atoms. They're on the same carbon, but different.
Okay. 55% of the points. Go on. Thank you. Same molecular formula. Now you can finish it. Yeah, come on, you know. Yeah, same molecular formula, but different spatial arrangement. Okay? They have the same connectivity, but different spatial arrangement. You got that? Okay? You got it. You know, part of it is you know enough to score, I don't know, anything between 60 and 90%. Can you communicate that? Yeah? Wouldn't you hate to understand it 90% and communicate only 50%? All right? Okay. So, clearly they're stereoisomers, but they're not mirror images. Therefore, they're not enantiomers. Okay? And there's that new word. They are diastereomers. All right? Okay. And I think with that, yeah, we're ready to go through the notes. That's it. A couple of other things though. Let me just change it for you. Okay. Let's change it to green. No, let's go for purple. Okay. Let me change this now to bromine. Change that to bromine. You got me? You got me? Okay. Now, it is still 2R, 3R, etc. That doesn't change. But the problem is, oh, well, I forgot to tell you diastereomers. But now, look at this. Now, I'm sorry, can I undo and let me just finish something? Undo ink stroke. No, I can't. If I erase it, it all goes away. Yeah, let's erase it. Let's screw it up completely. Let's not be half-hearted. Okay, so that's a chlorine, that's a chlorine, that's a chlorine, that's a chlorine, okay? And so here we said they are not mirror images, but they're stereoisomers, so they must be diastereomers. Okay? How about these two? What's their relationship? What do you think it is? Identical, enantiomers, or diastereomers? You think they're enantiomers? Okay. Why? Enantiomers are mirror images. So one way to look at it is this S chirality here becomes an R. This R becomes an S. Okay? So these are enantiomers. Enantiomers. Okay? What about these two then? What are these? They are diastereomers. You got that quickly, haven't you? Good. When you read the notes, it's good, isn't it? Yeah. All right. Yeah. I can tell you now, about 10 of you haven't even downloaded the notes. But if you read the notes, it's really good. Okay? All right. So these are diastereomers. Now, what you notice is that of these four, okay, we found an enantiomeric pair. What do you think their relationship is going to be? Yeah, very quickly. All right. So when you have two chiral centers, they actually break into two pairs of mirror images. And then when they are up against somebody that's not their mirror image partner, they're diastereomers. Is that easy? All right. Ready to go through the notes? One thing though, I'm going to change it now. You know what? You'll come to meso compounds when you get it. Okay. Let me just make sure the notes make sense now. I think we can go through this really quickly and then we can do some problems. Alright? So, first of all, as a general rule, when you have n number of chiral centers, you have up to 2 to the n. Okay? So if you had this compound, which we've just seen, you have 2 chiral centers. So the number of possible, please look at this, possible. Doesn't mean it has it. It just means it's possible. Structurally, it's possible. But then we're going to look at meso compounds. It would be 2 to the n, where n equals 2. So it's 2 to the 2 equals 4. All right? Okay. So if you were to have, say, a compound that's like this, let's make it horrible. Bromine, chlorine. Let's put another bromine there. How many stereoisomers could you possibly have? 8, yeah? And what are they? You know, they are going to be your R, 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 yeah? S, 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 etc. Does that make sense to you? It's just probability, isn't it? Okay, so you can have up to 8 isomers, but it's only possible. Okay? So that's what that says. And they fall into pairs. So within these 8, okay, let's call it 1, 2, 3, 4, 5, 6, 7, 8. Okay? The relationships are, if these are mirror pairs, if these are enantiomers, then one and all the other ones, what must they be? They must be diastereomers. Okay? So anything else that's not a mirror image is a diastereomer. Okay? For those of you doing cell biology, you come across the term an epimer. Yeah? Do you know what it is? Yeah, an epimer really is, sometimes with sugars, you can have many chiral centers. Supposing you had 4 of them, okay? If you had 4 of them, how many possibilities do you have? 16, okay? So if you had something that's got, I don't know, R, S, R, what would its enantiomer be? S, R, S, okay? And what if you had something like this, diastereomer? Okay, oh, anything really. Just screw that one up, keep that one the same, and keep that one the same. Does that make sense? That would be a diastereomer. An epimer, one possibility is like this. S, R, S, R. So what's happened there? Oh, I beg your pardon, I've got it the wrong way around. It's not when one of them, okay? It's when one of them is inverted. You see that one? Only one of them is inverted. Okay? Only one chiral center is inverted. And it's very critical because what we're saying is structure affects property. So when you have a large biomolecule, let's say, because of the number of chiral centers, there are lots of possibilities. Okay? However, when only one stereo center is different, can you see they've managed to be just 1 degree removed from enantiomers? Yeah? And very often drug interactions depends on mimicking, yeah, a receptor site and an active site. And when you mimic, you want to get close to what you're mimicking. Yeah? And so you're talking about degrees of structural difference. Molecules are identical. Molecules are mirror images. Molecules can be epimers. Does that make sense? Question? Okay. All right. So let's move on. Okay. And so diastereomers are stereoisomers that are not mirror images, that are not enantiomers. Okay. So you see how this statement holds then. The 2R and the 3R, these are enantiomers. Yeah. Okay. I think we're okay there. Let's move on. And here what they've done is, I didn't want you to make this model, but you see we've got the 2R and the 3S. Okay? And then across the mirror we've got the 2S and the 3S. So they're enantiomers. Work through this diagram and you'll see it should be fairly straightforward. Are we okay with that? Anybody got questions? No. Okay. Let's try problem 5.15 if it's suitable. I need to borrow somebody's book. Yeah. Give me a moment, okay? I'll come back to that. Now we have a problem. Alright? So, very quickly then, let's just assume that this one is, they've told you, right? This one's the R, and this one is the R, okay? So its mirror image must be S and S, which is what we've been told. Okay? So if you've got the RR, SS, this one, okay, you can see it's the R because all the groups are the same, plus it tells you anyway, yeah? But even if it didn't tell you, can you see this arrangement down here? They swapped over the hydroxy and the hydrogen. Hydroxy, hydrogen. So this is R, so therefore this one must be S. We okay with that? So you've got these ones here. So this is S, this is R. Right? So now, supposedly, these are enantiomers. Alright? And what about these? These are supposed to be another enantiomeric pair. Yeah? But the problem is, right at the beginning, remember we said a molecule can have chiral centers, but a molecule is not chiral. Because for a molecule to be chiral, it must have a plane of symmetry. Sorry, it must not have a plane of symmetry. Okay? So here what you have is, great, they are looking at each other across a mirror, but this is the same one. Do you see there's a plane of symmetry across here? Okay. So if I were to switch this one to You see, before I had two different chiral centers, okay, bromine and chlorine. And what they've done now is the top group and the bottom group is the same, okay, the OH and the OH. So what we do is let's switch that to a red one, all right? So this is one stereoisomer, and let's make sure I've got the other one. And now they're looking at each other at mirrors. Are you okay? Oops. Ah. Are they looking at each other across a mirror? No, they're not yet. Like this, okay? Are they looking at each other across a mirror? Yeah. Are you sure? Yeah. All right, all the reds are closest to me, furthest away from you. Okay? But let's examine each one of them. See this one? Do you see the plane of symmetry? Yeah. Yeah. And therefore, here, yes, they're mirror images, kinda, but they're not. I can flip this one round, and it's exactly the same. You got me? Or another way to show it, they were looking at each other like, look at each other, okay? They were looking at each other like this, all right? But because of symmetry, I can just twist this one round and now they're the same, okay? Yeah, and that's why we said when you have, say, so many chiral centers, you can have up to so many stereoisomers. Structurally, that's possible. However, some of them ends up being these identical compounds. And those identical compounds are called a meso compound. Okay? So what's a meso compound? It's a compound, don't like that color, let's do that. It's a compound that has chiral centers, but it's not chiral. Alright? Make sense? Okay. Let's push you. How about if I were to draw this one? Let's do this one. This one, okay. I would like you to assign stereochemistry. That's the first thing. The second thing, I want you to name its enantiomer. And for 3, I'm asking you, is this a meso compound? And then I'll show you how to quickly tell. Okay, let's try that, and then I'm going to pause you. Alright, how are we doing on the first one? Assign stereochemistry. Somebody give me the answers, please. 2R, 4S, is that right? Alright, we all agree? Okay, so name is enantiomer. Okay, so it would be 2S, 4R, yeah? Okay, so that would be the enantiomer. Okay, is this a meso compound? Yes. Okay, and how did you see it? There you go. Straightforward, isn't it? Okay, it's right there. And you know another way to see it? Yeah? Here, even if I didn't draw it, alright? Even if I just gave you this, and I just did this, and I told you it's 2R, 3S, you got me? By the time you've got that, if this is an R, this is an S. Is that right? 4S, sorry. Yeah? You know if this is the mirror, anything which is R on this side has to be S on that side. Yeah? So even without the name, even without the drawing, you can see it. Does that make sense? Yeah? This one here, this is an R, and if there's an internal mirror, then across the way it must be an S. Okay? Now this should make sense. How many chiral centers? Don't like that color anymore. 5 chiral centers. You got 4 chiral centers. Okay? How many chiral centers? A, B, C. I see 4, and that's probably because, okay, let's see. I see this one, yeah? Okay, did you see this one? Okay, who saw this one? Okay, this one is not. This one, look at it. These two groups are exactly the same. So you got this one, and you got this one, okay? Yeah. So, how many chiral centers? 4. So how many possibilities? 16, okay? Is there a mesoform? There might even be more than one. Yeah? Can you see if I call this 1, 2, 3, 4, just for simplicity's sake? Yeah? I really should call it, the longest chain is a 6, I know, yeah? But I'm just going to call the chiral, I'm just going to number the chiral centers, okay? So really, it should be if I have 1s, 2s, yeah? The chiral form has got to be 3r, 4r. Make sense? Yeah? If this doesn't make sense, make models and have a look. Alright? So chirality, especially when we're looking at biomolecules with a lot of symmetry, okay, and we're talking about a lot of carbohydrates, okay, it's a very powerful concept. Okay? So, you know, that's one form of it. You know, is there another form of it? Yeah, there probably is another form of it. I mean, how about the 1r, 2s, okay, and this would be 3s, 4r. Agreed? Oh, beg your pardon, I'm wrong. I am absolutely wrong. No, that's right. RS, that's right. 2s, this should be R. Yeah, because you're looking down this mirror. Okay, and this should be S. Agreed? Okay. So there's the mirror. So the 2 center, these 2 centers must be mirror images. And then the 4, the 1 and the 4, they must reflect each other. Okay? That's it. Should I try a problem? Okay. Let's try it. Let's see what they say in 517. Okay. Let's pause this. What about this one? Does that have a mesoform? Yeah? Yes or no? Okay. Yes on what conditions? For something to be a mesoform, what are all the conditions? There must be a plane of symmetry. Yeah. What else? It must have chiral centers. It must have more than one chiral centers. Otherwise, you could say something like this cannot be a mesoform because it doesn't even have chirality centers, okay? So, do we have chiral centers here? Yes, we do. Do we have a plane of symmetry? Clearly, straight down here, yeah? So we're okay. Now this one, you see this is just another stereoisomer of structure A. Is this a mesoform? No. Okay, it's got chiral centers. Okay, let's switch then. What about this one? Okay, is that a mesoform? Why not? There's no chiral centers. And you know, I gave you that multi-part question to ask you to go symmetrical disubstituted, symmetrical tetrasubstituted. I was setting you up to think about symmetry. Coming together? Okay, so that one's okay. What about this one? Is that a mesoform? Does it have chiral centers? It's all symmetrical, yeah. You see this one here? You see that symmetrical? Yeah. These two are the same. These two are the same, incidentally. Yeah. And this, you see this one is the same. You've got a methyl group, a hydrogen, but then these sides are the same, yeah? So it can't have a mesoform because it's not chiral. What about this one? This one's a bit harder to see, isn't it? Yeah? But how else can you attack it? You can't see the symmetry. You can make a model, yeah? But what else can you do? Rearrange it, yeah? Yeah? Okay, if you can mentally rearrange it, that's possible, yeah? You can make a model. So for this to be symmetry, what do these two have to be? They have to be opposite, don't they? So what can you do? Assign stereochemistry. That's one way to do it. So you can either visually twist this around, yeah, or you can make a model, or if you assign stereochemistry quickly, yeah, to make sure that if that's an R, this one needs to be an S, and this, or if the top one is an S, the bottom one needs to be an R. Simple, isn't it? And then don't forget to make sure that they've got the same groups around it, because it only works if the chirality center have the same groups. All right? Good. I'm done. I mean, you know, if you guys have gotten this, that's fine. Let's give you a peek ahead. Okay, and I hope next lecture the fun starts. Let's see. Okay. Yeah. All right. Say that again. This one? B does have chiral centers. Lower one? This one? Why doesn't this have a chiral center? So on this one here, so you got an OH group, yeah, you got a hydrogen, and then the left side, okay, and the right side, there's one side, there's the other side, they're exactly the same. Okay, yeah. Sorry, on Friday, I'm not going to start a new topic, okay? I'm going to slow down, but you're all finding, try the problems, do the homework. Even if you can't get it right, at least look over the homework problems. So on Wednesday, at least you know what questions to ask, okay? Quick question.
Question where you asked.
Should I deal with that later? Yeah. Okay. It's a spiral, okay? It's a spiral compound, okay? I wouldn't ask you to name that, but it's a spiral compound, okay? Hey, guys, bad news, okay? I'm going to finish on Wednesday on this chapter. Yes, you have a stereochemistry workshop next week in lab. In lecture on Friday, I'm going to start chapter 6, okay? So, anticipate that. So the sooner you get cracking with the rest of chapter 5 assignments, the better. Okay? Thank you.